What we're going to talk about in 5.4 is a very cool question. Can you find the length of the curve on a plane? Not a three-dimensional curve, we're not there yet. That'd be like a Calc 3 question, but a two-dimensional curve. So basically, take my favorite function ever, can you find the distance on the curve from A to B? Not just A, B minus A, not that. Can you find out how long this curve is? And the answer is, well, sure. But is this the way to do it?
Probably not.
35 centimeters, ha ha ha, I win. No, that's probably not the way that you can do it and be accurate. You can get approximation,
You
right?
can get a piece of string.
You could get a piece of string and try to fit it to that. You could. And then measure the string. But you're going to be off, aren't you? Be off a little bit. The string has some width to it, you're going to be curving it. It's going to be off a little bit. At least, and you're not going to be able to fit it perfect.
Volume divided by height?
Say what?
I said volume divided by height.
Not going to give you the length though. A volume divided by the height should give you an area of some sort. An area. Let me give you, maybe posit a different idea, okay? What if we were to take part of this curve, now maybe that's this part right here. How would you find, using the idea of some calculus, how would you find the length of something?
Change the backs, you can take the limit and then add them all together.
We're going to be using some sort of limit, sure. Well, what if I were to divide this up and go and make straight lines? Can you find the length of a straight line? You can get sound effects on that, right? Can you find the length of a straight line? Geez, I hope so. If you know the distance from here and the distance from here, you should be able to use Pythagorean theorem to find the distance of a straight line, right? Now, of course, that's going to be approximation. However, if we move this distance to here, all these distances really, really close, the length of the straight lines will be exactly the same as the length of those curves for those little teeny itty bitty pieces. You've seen the limit idea come back again? So here's our idea. Our idea is, let's go ahead and do the same exact thing we've been doing. Now, we don't care so much about the height. We don't. What we care about is this, that distance, and that distance. We're going to truncate all the curve. We're going to truncate it. Just make a straight line from this point to that point, where the function touches to where the next function, or where the vertical touches the function to where the next vertical touches the function, and try to find out where that is. So the idea is, let's cut these into small sections, and let's add those lengths together. That's the idea, very similar to areas, but we're not talking about areas, we're talking about lengths now. So this we don't care so much about. Just up here. Are you ready to go through and see how to do this? Ready? So if we call this x sub 1 the first cut, and x sub 2, then we're going to get all the way out to the x sub nth cut. Can I take one of these pieces and blow it up for you so you see what's really going on here? Let's take something that looks like, how about this very first piece? Now, I gotta be pretty general. I can't call this x sub 1, so I'm gonna call it x sub k. You guys are right with that one, x sub k. If that's x sub k, tell me how much that is. Very good, the previous one. Brilliant. Okay, now you know our goal, right? Our goal here is to do this. The goal is to find the length from here to here. That way when I make this distance really, 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 really small, It's going to very, very, very closely approximate that curve's length as well. Do you get the idea there? Okay. Now, how do you find the length? Ideas. This is kind of a secant line.
What's a summation? Make a 90-degree triangle. Use
Make a 90, oh, that's a great idea. Why don't we make a 90-degree triangle? Why don't we make a 90-degree triangle? Let's talk about this for a bit, just for a second. What's this distance? You're overthinking it. What's the distance every time we go from one cut to another? Yes. Mhm. How high is this from here to here?
F of x.
No, no, not f of x. You're close though, you have the idea.
F of x. Okay. F of x. Okay.
Yeah. Not sub k. K minus 1, yes. Do you notice that that's the height at that exact point? And if that's the function, that's going to be the height of that function there too. Now, what's the height here?
F of x of k minus f of x k minus.
That's the whole, I'm talking about the whole height. We're going to get here in just a second. So if this is f of x sub k, and this is f of x sub k minus 1, we already have the width of a triangle. We need to find the height of the triangle. That lets us use Pythagorean theorem and find the length of the hypotenuse. You follow me on this? So we're using Pythagorean theorem. This squared plus this squared equals this squared. That's going to be great. We'll call this L sub k for the length. What would this be? What's that distance?
Function f of x sub k minus f of x sub k minus 1.
Yep. F of x sub k minus f of x sub k minus, sure. If this is 10 and this is 7, that's 3. You just take and subtract them. The big height, that's this height right there. Minus the little height, since that's a 90-degree angle, 90-degree angle, that's got to be the exact same parallel line. You know that this height away from this height gives you that distance, and that's what we're talking about. Reach and feel okay with this so far. And if you handle that, we're almost done. Well, not really. But you have the idea now. You have the idea. Now, let's talk about Pythagorean theorem and what it does. Pythagorean theorem says a leg squared plus a leg squared equals a hypotenuse squared, and we have some symbols for all that stuff right now. Hypotenuse equals, let's see how I want to do it, a leg squared plus a leg squared just like that. Okay, real quickly, are you guys okay on getting this from here? Are you sure? You see where it's coming from? Do you see how L sub k is our hypotenuse? See?
Is that a delta at the end of it or an arrow? I think
Arrow?
it's fine.
Just an arrow. We're about to go further. Do you see how L sub k is our hypotenuse? Yes, no. Delta x is one of our legs. This is another one of our legs. F of x sub k minus f of x sub k minus 1. That's a leg, it's a distance. So this squared plus this squared equals hypotenuse squared. Quick head nod, you okay with it? Okay, cool. How do you get the square away from L sub k? Are you so far so good? You guys have any questions on this before I continue? Seriously, are there any questions on that before I continue? None on this is old stuff. You had your chance on that one. Now for the fun part. You ready for the fun part? You got to follow me on this. This is bringing us some, it's like regurgitating some stuff, and you're going to be like, oh no, throw it back. Just don't bring that up. But just wait. Now, do you recall what the mean value theorem says? Not a bit.
I remember that was like 4 weeks ago.
Oh, that was longer than that.
It was like 10 weeks ago.
Here's what the mean value theorem says. Basically, in layman's terms, we're layman. It says if I take the slope between 2 points, i.e. the slope between 2 points, then on this segment, the first derivative must equal that slope at some point between these two. Follow me again. The slope of this line is something, true? True. At some point between here and here, the slope of my function will equal the slope of that line. Agreed? And where that takes place will be between these 2 points. Somewhere on that interval. Do you understand that? Yeah, everybody. Here's what it says in math. It says this will equal, what's the slope of a function in terms of calculus? The what?
First derivative.
First derivative. First derivative. At some point, look, at some point
Arbitrary point.
between here and here. We don't know what it is, arbitrary point. At some point between there and there. Does it matter where it happens? I don't care. Why? Why don't I care? What's going to happen to these two numbers? Bam! Smash them together. That xk dot, the sum point, where the slope of my function equals the slope of my secant line, where that happens by the mean value theorem, it has to happen for a continuous function, and we're assuming this is a continuous function, that has to happen, we call it xk dot. It's going to be somewhere on this interval. This is all by the mean value theorem, by the way. By the mean value theorem. By the way, did you believe me? See what this stuff actually is? I hope you see what it is. This is the change in height. We already have this on the board, actually. This is the change in height over the change in width. That, by definition, is the slope. You see it? The slope between 2 points must equal the slope of the function at some point that's between those 2 points. That's what the mean value theorem says. Believe it or not, that's true. Do you got it? Now we're going to do some fancy dancy math. Wiggle, 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 wiggle. Okay, that's it. We're going to wiggle this around. Do you understand what x of k minus 1 is? Very good. So substituting, we're going to have that's delta x. Are we having fun yet? Are we having fun? This is not fun. It's awesome. Here's my goal, by the way. You don't know the goal. The goal is this thing sucks. I want to get rid of it. That's the goal. That thing sucks. So how do I get rid of it? Let's try to find this here. Do you see it? Solve for it. If I solve for this piece, I just multiply both sides by delta x. Okay, we've done a lot of math work. Do you feel okay with it so far? Raise your hand if you do feel okay with it so far. A lot of theory, right? We haven't done anything actually. Well, we manipulated it algebraically, but we haven't done an example yet. Here's what I'm going to do. I'm going to notice that this piece right here is the same as this piece right here. I'm going to put that thing in instead of it. So L sub k equals, we got the square root. Inside the square root, we have delta x squared plus This big fat piece of junk we're going to replace with this big fat piece of junk. Instead of this, we have f of x sub k minus f of x sub k minus 1. That's that. We're going to have f prime x sub k dot, or xk dot, times delta x. Don't forget it has to be squared. Are you still okay with it? You guys have any questions so far on it? You see where the stuff is coming from?
Doesn't seem a lot simpler that way though.
Well, there's not much we can do with this. There's something that we can do with that. That's what we're going to do right now. Oh, let's see. Let's do one more thing here. Let's break this up a little bit. Let's just do that. So far, so good? By the way, did you guys have any questions over here? Because I'm going to erase and continue. So you understood the idea of cutting it up, right? Finding the length of each segment using Pythagorean theorem. Now we're just working that down. So take note of that. Hopefully you have that. The important part was to get our substitution done from here to here. That was the idea. I guess I do have some room over here I can work on. So from here, do you see that we can factor out a delta x squared? So we're going to have 1 f prime of xk dot squared times delta x squared, but that is going to be in a big old bracket. I'm going to draw it in black so you can see a little bit better. If you factor out the delta x squared, you need a bracket around this whole thing, just like that. You okay with that? Now, roots are kind of awesome because you can split them apart by multiplication. So do you see that I can have a square root of this first thing times a square root of this second thing? But a square root of delta x squared will give you just delta x. So next step is going to be L sub k this times that. Notice how I'm putting the stop after the square root right there. We take the square root of delta x squared, it becomes delta x. The only reason why we can do this, ladies and gentlemen, please notice this, is because we were able to factor out the delta x squared from right here. We were able to factor it out, create a big bracket that's being multiplied, and you can split up multiplication. You can't split up addition. We could not have done it here. You can't just take square root and take square root. It doesn't happen. You have to factor it, split it off, do all that nonsense, and then you can do it. How do we feel okay with all we've done so far? Hey, that's the length. That's the length for one single section. Tell me how I find multiple sections.
Summation.
A summation would help me find multiple sections. Very good. So that's for one. So here's for all of them, but it's an approximation. How do I make it a better approximation? Yeah, as n goes to infinity, that means instead of just a few cuts within there, we're going to make an infinite number of cuts. That causes this distance, remember that was the distance between those points, to go to 0. It causes the arbitrary point to be smashed in between there. So yeah, you have a little distance because otherwise you can't find the length of that, right? You can't find the length of nothing. So it's a little distance, but it's so small, it doesn't make any difference between the actual line, the secant line, and the distance of our arc. So take a limit that L equals a limit of this thing. Now, when you take a limit, we've noticed just by practice what these pieces mean. Can you tell me what the limit of a sum becomes? And it goes from where you start to where you stop. The square root, hey, that's a square root. The 1 is a 1. Plus is a plus. F prime, look at, we're going to have a first derivative inside of our integral. Isn't that interesting? It's kind of weird. But that's what that says. It says you have a first derivative of a function. What's xk dot become? Just s. Don't forget to square it. And what does the delta x become? That's it. What we've just done is something that's freaking awesome. We just found the length of a curve between 2 points. Is that not cool? Very cool. We know how to find the length of a curve. You draw me a curve, if you know the function to it, we find the length. Now that clock's a little fast. We're going to do one example because I don't want to leave you hanging on this. I'll explain something in a little while about why we are going to go over a little bit. But stick with me, please. Don't hate. Trust me, I'm doing you a favor. So this is the length of a curve. Note that this is along which axis? You feel long? Shoot, I can't even spell today. Yes?
Why did you say that first?
So these are back to matching up. Along the x in terms of x, along the y in terms of y. It matches. I'll give you one example here. Let's say I would like you to find the length of the curve. This. On that. I want to right now just practice setting this up, making sure we see where these pieces are coming from. That's important for us to do. So, what's the first thing, if we're going along, well, it doesn't really matter, let me put it another way. Whether you think of this in terms of x or y, the length of the curve doesn't change. Length of the curve is the length of the curve. So do what's easiest for you. The volume of a region is a volume of a region, right? Doesn't matter what you do it in as long as you do it correctly. So whether you want to treat this along the x-axis or along the y-axis doesn't matter. Use what's given to you. Now this is in terms of x. We're going to do it along the x-axis. Now the process doesn't change at all, really. There's no x's or y's in here. That everything's coming from your function, so it's good to go. Looking at our formula, what's the first thing you're going to do? Say it again? Yeah, you got to have a derivative. That's nice. Find a derivative. If I do the derivative, don't forget how to do a darn derivative, all right? Some people just miss the little constants. The little constants are, man, it's a simple mistake. No, it's killing you. Not simple anymore. 3 comes down, no more 1/3. You just get x squared. That is, well, negative 1/4, oh, well, negative 1 over 4x squared. Can someone double check that for me, please? It's right, isn't it? So find your derivative. Notice I moved my x up. I left the 1/4 alone. Move my x up. Negative 1 comes down in front. It's negative 1/4. Subtract from the exponent becomes negative 2. Move it back down. You get over x squared. If we set up our integral. Where are we starting?
1 through 3.
On inside the integral, we're going to have a square root. We're going to have 1 plus. On the inside of that square root, you're going to have x squared minus 1 over 4x squared dx. How many will feel okay with the setup, at least the setup? What's your next step? Remember, these have to work out, have to be able to be manipulated, or you can't do them. There's not going to be a substitution. There's nothing to substitute. Okay, they have to be algebraically manipulated for this class in order for you to even do them. So what are you going to do first? Squared. Yeah, you're going to square. What you're going to get is x to the 4th minus 1/2 x squared. No, I'm sorry, I need to work it out. I can't do that one in my head.
116 minus x to the 4th minus 116. Or not minus, yeah. And then x to the 4th.
This is right? 1/4 minus 1/4 is just minus 1/2. Okay. I think we'll leave it for there. We'll talk about how to do the rest of this later. I won't hold you too long. Let's continue our problem. We're finding the length of a curve between 2 points. So we have, well, I think I derived that for you last time, didn't I? Made that up for you? Cool. So we're doing an integral from our two, bounds. And we're going to go square root of 1 plus the derivative of the function squared. Don't forget that's a derivative of the function. Don't forget to square it. Dx. So our function is 1/3 x cubed plus 1 over 4x. We've gone ahead and found the first derivative. So what we're doing here is we're just taking this first derivative, plugging it into this function, or this formula, and we have this integral that's left. After that, it's really just algebraic manipulation. The integral is not going to be hard in general. It means you have to manipulate it, though, algebraically before you can even do the integral. See, right now, you're stuck. I mean, you can't do anything with that. You've got to completely break this thing down and see exactly what we can do. You follow me on that? So, we square this, we get x to the 4th minus 1/2 plus 1 over 16x to the 4th. So that's where that's coming from. We're just expanding that, just squaring it, distributing, combine some like terms. You're going to get this thing. Did you follow me on this so far? Now, let's continue going. Let's get rid of some of those parentheses. We have 1 plus this. The parentheses really aren't doing much. Really aren't doing much there. If it was a minus, yes, it would change every sign. But with that plus, not so much. Well, let's continue rolling here. We'll still be going from 1 to 3. We'll still have a square root and a dx. Inside the square root, I'm going to combine some like terms. I'm going to have 1 minus 1/2 is going to give me 1/2. I'm going to have the x to the 4th. And I'm going to have 1 over 16 x to the 4th dx. Quick head nod if you're okay getting that far algebraically. Now here's the deal. This thing right now just completely sucks. But you can't split up square roots by addition, can you? So you can't just start taking square roots of things, can you? So somehow, what you need to do, anytime you see these multiple terms in here, and there's no substitution, notice there's no x's at all. No substitution is going to work for you here. Combine everything. Combine it all. And see if somehow you can manipulate the fact that the square root can be broken up across a quotient to try to simplify this expression. So, in other words, when we have these fractions and all these terms, you're going to have to find a common denominator. You're going to have to somehow put all of these things together and then see what you get. If it can be done, it will work out. Okay, if it can be done. Some of them, I mean, if I give you just a random function, it's not going to happen. These are very specific functions. So let's find a common denominator. What is your common denominator between 1/2 x to the fourth and 1 over 16x to the fourth?
16x to the fourth.
Very good. So we're going to go ahead and make all these fractions equivalent, but have the denominator of 16x to the fourth. What that means is we're going to get, let's go careful on this thing. 1/2 is the same thing as 8x to the fourth over 16 x to the fourth. 1/2 is this. Do you believe me? I hope so. I'm the teacher. You should believe me. Although maybe I've lost your trust. Are you guys okay getting from the 1/2 to the 8x to the fourth over 16x to the fourth? You see it is 1/2, right? In other words, we're just multiplying by 8x to the fourth over 8x to the fourth. That's it. Plus this thing, x to the fourth, is the same thing as 16x to the eighth over 16x to the fourth. That still equals x to the fourth. So that's an equivalent expression as well. This is this. Plus, nothing I need to do there. It's already the denominator that I want. 1 over 16x to the fourth. Tie it all up with a dx. And switch some pens so we get a different step here. So that's the integral from 1 to 3. Big square root. Check out what happens. Now that I have that common denominator, I can make everything as one fraction with the denominator of 16x to the fourth on the bottom of a fraction. Also, I'm going to choose to write these in a different order. I'm going to write the 16x to the eighth, then the 8x to the fourth, and then the 1. Are you guys okay with that? All algebra right now. All algebra. 16x to the eighth. 8x to the fourth, yes. Plus 1, yes. All over our common denominator, we're good to go. Do you feel okay with it so far? Now, I told you this is kind of a special function because when you look at it, notice how now I can break up my square root by the numerator and the denominator. So I'm going to move up here. That's 1 to 3. Square root of 16x to the fourth, that's denominator, sure. And also the square root of 16x to the eighth plus 8x to the fourth plus 1. You didn't know there's going to be so much algebra in this stuff, did you? Expected hard integrals, they're not hard integrals. They're hard algebra to get to an integral you can actually do. It's different, weird. Do you feel still all right with getting that far? Tell me some cool things that happen, specifically with the denominator. Denominator.
It squares out.
It does. Yeah, what's the square root of 16?
4 squared.
Cool. X to the what now?
Square.
Good, because you have a power of 1/2. Numbers to the, excuse me, exponents you multiply, so you have a to the fourth to the 1/2, or a square root of x to the fourth. Either way, you're going to get x squared out of that. So denominator, not bad at all. Four x squared dx. Very cool. Let's work a little bit more on the numerator. In order for this to work out nicely for us, something has to happen. We either have to have a substitution that's present, have to, or we need to create some sort of a square. Why square? Yeah, so the square root will actually work here. Now, when you look at that, 16x to the eighth plus 8x to the fourth plus 1, it might not be easy to see, but that's a perfect square. Do you guys see the perfect square out of that? That is a 4x to the fourth plus 1 squared. Four x to the fourth plus 1 squared. Let's verify that just for a second. 4x to the fourth times 4x to the fourth is 16x to the eighth. Great. We're going to have 2 4x to the fourth, so that's 8x to the fourth, and then the plus 1 on the back end. So that's the appropriate factorization. If you wanted to, you could make a substitution for x to the fourth equals y and substitute it that way, and then the factorization becomes a little bit easier since you don't have those eighth powers and fourth powers. It's a little bit hard to think of, but that's certainly the appropriate factorization. Why is that so important for us to do?
Square root cancel out the square root.
Exactly. That has to happen, or you gotta be able to find a substitution for that to work. Otherwise, you're gonna be kind of stuck. So, square and square root, those are inverse operations, those things are gone. We have 4x to the fourth plus 1 over 4x squared dx. Hey, we're almost home free. We got something that looks really nice. What now?
Move the denominator to the top.
You could. I'm going to do it a little different way, but you could do that. If you did that, though, notice you'd have parentheses times 4x squared. You'd have 1/4, and then x to the negative 2. So you'd have something a little bit awkward to deal with. Other ideas? Split it up. Probably. Substitution? No. No, don't do a substitution unless you absolutely have to. Split things up if it's easy to do so. So here, yes, split it up. Remember these when I gave them to you? Like the first time we ever dealt with integrals, I gave you something like that. It had t though, like t cubed plus 1 over t squared or something. I said think a little bit more about these things, split them up when you can, because if you have like variables, you can combine those things. So 4x to the fourth over 4x squared, yes. Plus that. So on a roll. Let's simplify them a little bit. We got 4x to the fourth over 4x squared. That's going to give you x squared. When you do the 1 over 4x squared, please don't make the mistake of taking the 4 with the x squared. That doesn't happen. The 4 stays on the denominator. Do you follow? It doesn't have a negative exponent. It doesn't even have an exponent. It's going to be x to the negative 2 over 4. That's the appropriate way to do that integral. You take the 4 up there, you're going to be off by a factor, by a large factor. You don't want to do that. Do you see why the 4 stays down there? Okay. Can you do the integral? It's not too bad. Not too bad at all, really. When we think about it, we're going to have x to the third over 3. That's an easy one. X to the third over 3. Plus, watch carefully. Remember that with integrals, you are adding, you're not subtracting. So can you please tell me, what does x to the negative 2 become? Perfect. Over what? Negative 4. Do you see where the negative 4 is coming from? Get the negative 1 times the 4, that's negative 4. Before you go and evaluate, take care of this mess. Make it look prettier right here. This is going to be x to the third over 3. We're going to have a minus 1 over 4x. Minus 1 over 4x. Yes, no? Where's going to feel okay getting all that way down that far? Cool. Hey, it's just evaluation for this. We got to go from 1 to 3. We'll plug in the 3 first, so that's going to be 3 cubed over 3 minus 1 over 4 times 3 minus, remember we have a 1 right now, you can't just put a 0 at the end, we have a 1. So you have 1/3 minus 1/4. If you do 9 minus 1/12 minus 1/3 plus 1/4, see where the plus 1/4 is coming from, first of all? Can someone do that on a calculator, see what you get? Okay. Common denominator is 12 if you want to do it that way. 108 over 12 minus 1/12 minus 4/12 plus 3/12. Huh? 53 over 6? Yeah, 53 over 6. What's that 53 over 6? The length, that's crazy. But we just found the length of this curve, right? It took us a long way to do it. But most of it is algebra. The only calculus you actually get to do is plug in the formula in. And from right here, let's see, right here to right here. That's it. After that, algebra, 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 evaluation, evaluation. So that's really what this is all about, is being able to use that formula, identify what goes where, and find the length out of that thing. So we found a length of 53 over 6. If it's in inches, it's inches long. It's kind of cool. It's really unique that we're able to do that. To take some random function, actually it's not very random, it's a specific function, because some of these things don't work out, and find the length of it, which is neat. How many were able to understand the example? Would you like one more?
Yes.
Any questions before I erase it all? All right. Okay, so let's do this one. F of x is now x to the 3 halves. From 1, 1 to 2, comma 2 root 2. You ready for this one? I hope so. Well, I want you to help me. I want you to tell me what I should do first. If I'm trying to find the length, what should I do first?
Take the derivative.
Very good, take the derivative. Am I worried about changing this into certain terms? Like, do I want to change it into terms of y or x depending on length? The length's going to be the same no matter whether you have this in terms of x or in terms of y, so it really doesn't matter. I'm going to show you in a little bit that it's going to come up with the exact same measurement, either way that you do this, okay? So whatever it is, it's fine. Just make sure that you have it in some terms. So y equals, this happens to be in terms of x. Maybe we write a y if you want. Y equals x to the 3 halves. That's in terms of x. Leave it in terms of x, it's okay. Taking a derivative, great. First derivative, everybody, what's the first derivative of that thing, please? 3 halves, don't forget the 3 halves, that would blow your problem up. 3 halves, x to the what? 1 half, very good. So our length is an integral from, now, this is the only place where you gotta be a little careful. What is your function in terms of? Is it in terms of y or in terms of x?
Terms of x.
Very good, it's in terms of x. So what are our bounds going to be? X's or y's? What's your function in terms of? Are you going to plug y's into x's? I hope not. So what are your bounds going to be in terms of? X's. You have in terms of x, right? This has an x in it. So am I going to go from 1 to 2 or 1 to 2 root 2? 1 to 2, because those are my x's. Wouldn't matter here, right? X and y is the same there, but here it definitely would make a difference. So because I'm in terms of x right now, I'm going to go from 1 to 2, square root, 1 plus, I've already taken the first derivative, we've got 3 halves, x to the 1 half, don't forget to square it, dx. Are you okay on the setup, ladies and gentlemen? Honestly, are you okay with it? Okay. That's the calculus. We're going to have a whole bunch of algebra and then a little bit more calculus. Let's see if we can work through this thing. What's the first thing we're going to do? Help me out, come on.
Square f of x.
Pretty sure that's going to be what?
9/4
x. I like it.
One to two, 1 to 3.
Oh, what did I do?
Your integral to 2. Your bounds.
I got excited. What now? What now? Think back to the previous problem. Think back to the previous problem. See what?
Find a common denominator.
Find a common denominator. Do we have a denominator right now? Yes, we do. Actually, you know what? Can we make this a little easier? Instead of doing all that, can we make it a little easier? Would you mind if I made it a little easier? Because we can do all that and you're still going to have the same problem. However, I want you to think about this for a second. Would a substitution work?
Yeah.
Tell me something. What's the derivative of this whole thing right here? 9/4. Do we care about constants when we're doing substitution? So would a substitution work? So don't forget about substitutions, that's going to work. If you found the common denominator would work out, the common denominator is 4, what you're going to get is 4 plus 9x over 4, that would be the square root of 2, but you're left with 4 plus 9x. You're still going to have, think about that for a second. Please just think through this in your head. If you find a common denominator, you have 4 over 4, write it if you want. You have 4 over 4 plus 9/4, right? You have that. When you do this, you're going to have 4 plus 9x over 4. You're going to be pulling out a 2 right there. You clear on that one? You're still going to have the 4 plus 9x in there. You're still going to need a substitution where you have to have a constant of 9. The 9 is going to be somewhere in this problem as well. So we can do a substitution now. It's going to work out exactly the same. Exactly the same. You want to see the substitution or you want to do it the other way? You're going to have a substitution either way. Do you see why you're going to have a substitution either way?
Yeah.
Let's do the substitution.
I think so.
Shouldn't it be 2 root 2 instead of 2?
Well, explain to me why that's not the case. Someone else explain why I have a 2 and not a 2 root 2.
Because the 2 is the x and it's in terms of x.
Very good. Did that make sense? If we have du equals 9/4 dx, if we reciprocate it, we get 4/9 du equals dx. Well, let's keep going with that. That's great. We got 1 to 2. We've got, what was our u? Use the whole thing. So what's our integral become if I take u to be 1 plus 9/4 x? Say what? I'm going to leave it the square root of u for right now. But we have the square root, just so you see where it's coming from, the square root of u, that's our entire u from right here. Also we have, instead of dx, what are we going to put? Don't forget the 4/9 du. Tell me one more thing I could do right now if I wanted to.
Pull the 4 out.
Say what?
Pull the 4 out.
Yes, I could pull the 4/9 out. What else?
Change the bounds.
I could change the bounds. Remember that with substitution you can change the bounds. Do you want to do that now or do you want to do it later? If I don't change the bounds now, if I leave it 1, 2, notice I will have to plug this back into u before I evaluate. Do you remember doing that? So it's one or the other. You either leave it like it is, which is kind of not correct because you're saying x's and u's, then do the whole integral and then plug this back in, that's okay. Or you can change the bounds now and we're going to change 2 and 1 to something else. Let's try that. So changing bounds. So I'm going to erase this real quick. When x is 2, how much do we get for u? 11 over 2? Okay. Let me get a double check on that as well. 11 over 2.
Yeah.
How about when x is 1, how much do we get?
13.
Perfect. Make sure these go in the right spot. So for the 2, instead of 2, we've just changed our bounds. Basically what you do is you take your 2, you plug it in for your x, it's going to give you out a u. So our 2 became 11 over 2. Same thing here, we plug in our 1, gives you out a u. Our 1 became 13 over 4. Now I'm going to do what Sarah said. She said, let's pull the 4/9 out. I like that. So we're going to have 4/9 integral from 13 over 4 to 11 over 2. And I'm going to do what Joe said, which said change the square root of u to u to the 1/2 du. Hey, hard integral, easy integral, what do you think? Pretty easy. Pretty easy, yeah. So we'll have the 4/9, but don't lose that 4/9. We have u to the 3/2 over 3/2. I'll evaluate in just a minute. Notice that we add 1 to the 1/2, you get 3/2 over 3/2. Be careful on making this a little bit prettier. You'll have 4/9 times 2 u to the 3/2 over 3. Still okay getting that far? Now, we're going to have 8 over 27. U to the 3/2. Do I need to put this back into this? No, because I changed the balance. It's great. All I want to do is evaluate from some really nasty numbers, actually. Really nasty numbers. You got 11 over 2. You got 13 over 4. Whew. Let's see what that thing works out as. So, 8 over 27. What do you say we leave that up front and don't deal with it for right now? Let's just plug in 11 over 2 to the 3/2. And 13 over 4 to the 3/2. Still okay with it? I'm not. It's horrible. It looks ridiculous. Oh man. Well, now we get to do 11 to 3/2 over 2 to 3/2. We get to do 13 to 3/2 over 4 to 3/2. Can you give me 11 to the 3rd power, please? Because I can't do that in my head.
1,331.
You know what, maybe I'll write it like this to keep it a little bit easier. Is it okay if I write it 11 squared times 11 for you? That's still true, isn't it? Okay, and I'm going to do the same thing here. 2 squared times 2 minus, I'm going to do 13 squared times 13. And this is just going to be 8.
It's like you just pulled
Which
that
one
out.
can go along?
You can do that if you really want. But it's going to be the same thing. It's going to be the same thing.
This problem just took a turn for the worse.
Isn't it the same thing? 4 to the 3/2 power, square root of 4 is 2, 2 to the 3rd power is 8, so you get denominator of 8 right there. You still okay so far? Super duper. Alright. Super fun. Okay, let's see here. So we have 8 over 27. We've got 11 root 11 over 2 root 2. We have 13 root 13 over 8. Awesome, awesome. Still very cool. How do you get those together? You do. Probably the first thing I would do is just deal with this root 2. Rationalize that. If I rationalize, I'll multiply by the root 2 of the root 2 and also 4 over 4 to get a common denominator of 8. So I'll show you what I mean by that. Fancy math, I suppose, but still basic algebra. Four root 2. 4 root 2.
5, 4. 5, 4.
Then you come to number 8.
I think that will. Hang on. 2 root 2.
Yeah. Don't you always use the same one for your problem?
You don't, for rationalizing, you don't need to worry about that 2, it's just the root 2. So rationalizing, it's just the root 2. I'm also trying to get a common denominator of 8 though, so I'm going to have 2 times 2, which gives me 4, times 2, which gives me 8. So I'm doing 2 things at once right here. Getting the common denominator and rationalizing, okay? Yes, no?
Yes.
Well, the problem's easy. It's a piece of cake. It's integral of the square root of u. The evaluation sucks. It's horrible.
Was that intentional or accidental?
You know, the numbers just don't work out nice on these. They really don't. I mean, you get some whacked out. You're going to see this. It's crazy. Weird things. But think about it. I mean, should the length of a line be something like 7? No.
Yes.
Unless it's straight. I mean, come on. It's not going to be that. 22 root 22 over 8 minus 13 root 13 over 8. We're almost done though. Just stick with it. You're going to get 8/27. 22 root 22 minus 13 root 13 over 8. Tell me what happens.
8.
I like that. Please leave that. Just leave it like that. That's it.
That's
Now,
close enough.
If you want to evaluate, you're going to get something like, you could evaluate, couldn't you? 22 times root 22 minus 13 times root 13, all over 27. You get 2.09 is the answer. It's about 2.09. So all this work, we found the length of a line though, didn't we? This is the exact. That's exact. It's approximately, if I did it right earlier, 2.09, whatever the units are. But you are finding the length of a
When you
line.
guys start dealing with numbers like this, you want to use decimals. Use the approximation.
But as soon as you start using approximations more and more, your problems get more and more off. More and more off. So if I approximated here, and then approximated like, well that would be, you know, not an approximation, but if I approximated here and then subtracting, approximated and approximated and approximated, you're rounding around, it's never a good thing. You're going to be off. How many people feel okay with this so far? Now, would you like to do this in terms of y?
No.
Just see how it goes. Okay?
No, not really.
I don't either, but I'm going to show you.
I laughed all the time.
That's a shame. That was so nicely done.
Should have taken a picture.
It's in my head. I didn't take a picture.
Oh, that's right. Yeah.
Should have taken a picture. Now, if I want to do this along, treating this in terms of y, I've got to solve for the x. So, in other words, I would square and take a cube root. So this would mean that x would equal y to the 2/3 power. Y to the 2/3 power. Are you okay with that? You sure? So if x equals 3, if y equals x to the 3/2, x equals y to the 2/3. You cube it, you cube root it, and you square it. That's what that would be. Now, someone tell me the next step.
On your derivative.
And that's why it's nasty. The negative 1/3 causes you a lot more pain and suffering. Okay?
I was going to be 2 to the power square root of 2, and pounds was really causing pain.
No, not pain. Not there.
Oh.
Maybe a little. Are you okay with the derivative though? You see where it's coming from. You bring in 2/3, subtract 1 from it, you negative 1/3. We can actually set it up right now. We got 1 to 2. 1 to 2?
No.
2. Y. In terms of y now. That's exactly right. So this is really why I wanted to do the problem, so you see that. Watch out for what you're in terms of. If it's in terms of y, you need y's. If it's in terms of x, you need x's. 1 plus the derivative of x squared. 2/3 y to the negative 1/3 squared. D what?
Y.
Good. Now, unfortunately for us, do you see the problem that we have that we didn't have previously? The problem before was nice, because it was a 1/2 and we square 1/2, it goes away. It's just y. This is a problem. Do you see why that's a problem? You cannot do a substitution here. Do you see why? If you do a substitution, you end up still having a y in there, and there's no y to get rid of. There's nothing. So that's not going to work. What is going to work is very similar to what we did in the first problem. Try to get a common denominator, try to break that off, and then see what you have, okay? So that's the process for right now. I want to show you because I know that some of you think I give you some homework problems which are much more brutal than the ones I give you. This is going to be a pretty brutal problem, so at least you're going to get it right now. This is 1 to square root of 2 root 2. What we're going to do, I'm going to kind of go a little quickly through this, just so you're seeing it quickly, I suppose. So we can get done with more things. But all of it's basic algebra. And again, I give you some nice numbers. If you look at the square root of 9y to the 2/3 right here, that's a square root of something that's essentially being squared. What this is 3y to the 1/3. Do a couple things here. I'm going to pull the 1/3 out. I'm going to move the y to the 1/3 up here. And even though it doesn't look better, it is. It is. Firstly, it's all algebra. Can you follow the algebra? Raise your hand if you're okay with that so far. It's all algebra. Now, why is that better? You can do a substitution. Check out the derivative of this. The derivative of that is going to have a y to the negative 1/3, isn't it? There's a y to the negative 1/3. It's going to work. So now we get to do our substitution, and we're going to change some balance. If we do substitution, du equals 2/3 times 9. That gives you 6. So what this means is du over 6y to the negative 1/3 equals dx. Can you guys follow that as well? We take our derivative just like you know how to do. 9 times 2/3 is 6. That's 18 over 3, that's 6. Y to the negative 1/3, sure. Solve for dx, just divide that. And now we're ready to do our substitution. but we want to change some bounds as well. So let's practice doing that. We want x, when x equals 2, y. When y equals 2 root 2, and we want when y equals 1.
Shouldn't
We want to
that
find
be
out.
dy?
Say what now?
Shouldn't it be
You know what,
dy?
you're right, I'm
Yeah.
sorry. dy. Very good. I guess we are in terms of y, aren't we? Thank you, sir. Put a little overboard there. So 2 root 2, when y equals 2 root 2, let's plug that in. So 2 root 2, you're going to square it and take the cube root of it. Oh my gosh. 8, 2, 18, 22? Pretty sure it's 22. You don't believe me, do you?
I'm trusting you blindly.
Just try it. Well, let's think about it. Not just do it in your head. Think about it. 2 root 2, square 2 root 2. You get 4 times 2 is just 8. Take a cube root of 8, you get 2 times 9 is? You can't do that in one hand, thankfully. 18 plus 4 is? I can do that one. 22. 1. 1's better. What's 1 to the 2/3?
1.
Times 9. 9 plus 4. The bounds are actually nicer here. See some numbers that are familiar? 1/3. Not from 1 to 2 root 2 anymore, from 13 to 22. We just changed bounds. We're not in terms of y, we're now in terms of u. This is y to the negative 1/3. This is the square root of, we picked that for our u. Instead of dy, we have du over 6y to the negative 1/3. We're almost home free. We're so close. This, gone. Pull out the 1/6. Don't forget about that 1/6. We have 1/3 and we have 1/6. What's it going to become?
20.
Very good. (13 to 22) u to the 1/2 du. Again, the integrals are easy. They are. They're not hard. You get 1/18 u to the, what is it?
Oh, or you did interview 3 times.
Over 3/2. (118) times 2/3 u to the 3/2. Yes, no? And we're going to evaluate from 13 to 27. No need to plug our y's back into here. No need at all. What did I do? Oh, sorry, I saw that. Okie dokie, no need to plug that back in. But check it out. If you plug in the 22, you have 22 to the 3/2 power. That's 22 root 22. You plug in the 13, you have 13 3/2 power. It's 13 root 13 all over 27. Same answer. Which way's easier? I don't know. I don't care. They're both about the same. I'd say the first one's probably easier because you can see a substitution very quickly. You don't have to do any algebra ahead of time. This one you have a lot of algebra to do, but then your evaluation's a piece of cake. Last one, the evaluation sucked. Oh man, that was really hard. This one, evaluation is really easy, but the work on it was hard. So it depends on where you want to do your work, I guess. You're going to get the same thing. You're going to do the same work. How many people feel okay with what we talked about so far? Okay. I need to introduce to you one more concept today. Here's the concept. I want you to imagine my famous curve. I want you to imagine my famous curve I want you to revolve it around the x-axis. Of course, we have this before, right? You've seen that. You get this sort of vase-looking thing on its side. Now, we've been able to find the length of the curve. We've been able to find the volume of this figure. What if I ask you not for the volume anymore, but I ask you for the surface area? Basically, how much wrapping paper exactly would it take to cover that figure? So not volume, not how much it would hold, how much surface area you would need to make it. How much surface it has.
On the outside or the inside as well?
The outside,
Okay.
covering of the outside. The inside we're going to consider to be solid. Okay, so it's a solid. But we're saying how much wrapping paper would it take if you were going to give us someone as a present, because you didn't have to cover the top and the bottom. Well, tell me something, what's the cross section?
R squared.
No, that would be the area. What's the cross section? Cross section is a circle. The surface area of the cross section would be, of course, pi r squared. But I'm not asking for the area, am I? I'm asking for what does it have to do with going around something? The circumference. Can you find the circumference of a circle? What is it?
2 pi r.
So if I take a cross section and find the circumference, and I do that at every little point, and add up all those circumferences throughout the whole length, can you see that I'm going to get the surface area of this figure? So our idea here is to take the circumference times the length and integrate it. Now we've already found the length. We just need to incorporate what the circumference is. It'll be very, very quick and easy next time. I'll show you how to do that. I'll give you maybe 1 or 2 examples, and that will be it. Okay, so we're all alone. There's no class in here today, but I'm going to give you a pretty thorough explanation on how to find the surface area of revolution. The idea is start with a function, just my famous function, and we're going to revolve that around the x-axis and try to find the surface area of the solid that we create. So basically, how much wrapping paper would you need to cover this entire figure on the outside? We're not going to include the ends, so we're going to leave those open, but basically how much wrapping paper around. The ends would be just a basic geometry problem. Area of a circle, area of a circle. So we're gonna not do that. But we are talking about the surface area of that figure. Now I want to kind of posit this, that the surface area is a combination of the circumference of a circle times its length. So when you think of surface area, it would be how far around you have to go at each little place on this figure that add up all of those surface areas, an infinite number of them, and you're going to get the surface area of the whole entire figure. So the idea is surface area equals circumference times length. Well, if you think about it, what shape are we making here? What's the cross section of any of these cuttings? And when you think about it, you say, well, yeah, of course, it's a circle. What's the circumference of a circle? And we know that is 2 pi r. So we're going to get circumference times length, 2 pi r times whatever the length happens to be. Now, if you think back, you watch the previous videos, we know that we've already done length. We know that length is actually the square root of 1 f prime of x, and we'll have a dx at the squared, sorry. And we'll have a dx at the very end. 2 pi r, think about what the radius actually is. The radius is the distance from here to here at any given point. The distance from the x-axis to the function is the function. You plug in whatever the x is, it's going to give you the height. So the radius in our case is simply f of x. So we have 2 pi f of x. What that means is that for us to find, and then we're going to integrate, of course, at every single point. So for us to find the surface area is going to equal an integral from where we start to to where we stop of 2 pi, that's coming from the circumference, f of x times 1 plus f prime of x squared dx. I hope that you can see where the formula is coming from. It is circumference, area around, or sorry, the distance around a circle, times the length, how many little circles you have to add up, how many surface areas. So here we have circumference, we have length, we've already made this up. That's how we're going to find surface area. Now, I'm about to give you a much more in-depth explanation. So remember this formula. I'm going to give you the calculus behind it all. So here we go. As with anything involving our calculus, the idea is, can you make little cuts and make those cuts go very, very, very small and then add them all together with a limit? Oh, sorry, add them all together with the sum and take the limit of that sum, saying I'm not going to add just a few of them, I'm going to add an infinite number of them. So basically we start off just like we started the area problem, just like we started the volume problem with disc and washers. Like anything else, we're going to make little cuts. And we can call them x sub 1, x sub 2, and so on and so on and so on. Now, each of those cuts, how we found the length of it, how we found the length of the curve, was that we took and we kind of truncated that curve. We cut it off. And we found the length of each of these straight lines, because we know how to find the length of the line. What we didn't know how to find was the length of the curve. Now that we do, well, we can have that. Now notice, when I take the length of the line, and I revolve it around the x-axis like this, when I revolve that around, what it's going to create are all these figures that have some surface area that's flat. We're going to have a flat surface area. Now, we use the length of this line to approximate the length of the curve. What we're going to do now is find the surface area of, it's called the frustum. It's the surface area of the flat part to approximate the surface area of the curved part. So all these cuts make all these cuts over here. And so on and so on. But that's not exactly it. You see, since we truncated this line, we truncated that function at every single cutting, we're going to do the same thing here. And what we're going to end up with is this figure. That would be straight. Straight, straight. Same thing there. So we basically change a nice curve into a whole bunch of little pieces added together, all these frustrums added together. They're flat-sided, almost like, from the side it would kind of look like a trapezoid almost. You'd have this perpendicular, and then these angles going up. Now we're going to take a look at one of these frustrum. So notice what I've done. I've just taken one of these things, I've pulled it off to the side. Here's our goal. Our goal is to find the surface area of that piece, of this piece, and then add all of the little frustrums together, all the little pieces together. Well, let's think about that for just a second. First thing. If that's our x-axis, where does our cut start and where does our cut stop? Now we have to be very general in this. I can't call it A, I can't call it x sub 1, x sub 2. I need to call it x sub k. And if I do that, what's the one right before x sub k? Well, it's just the previous one, so x sub k minus 1. So we now know where the frustum is going to start and where it's going to stop, where the surface area is going to start and where it's going to stop. Now, in order to find the surface area, I have to just give it to you, but if you look it up in kind of an advanced geometry book, you're going to find out that this is true. If I find the surface area of a frustum, that's just the outside region. If I find the surface area of that outside region, that means this angled part that's coming out at you. What it is pi r1 plus r2 times the length. That's the formula for surface area. Now, of course, I'm doing this for each and every one of these little frustrums, each and every one of these pieces. So I'm going to say, not just surface area in general, surface area for the kth one. Pi is a constant, that doesn't change, but the radius for the kth one, the other radius for the kth one, and the length at the kth frustrum. Now let's talk and try to figure out if we can figure out what r sub 1 k is and what r sub 2 k is. L sub k, we already have that one, but we're going to worry about these two things. So if I call this R1, and I call this R2, can you tell me how much R1 is? I know you can't because you're on the video, but let's just think about it for a second. If I'm trying to find R1, think about what we're doing. We're taking and we're cutting from here to here on the function. Notice it's a secant line. So the height at this point is the function height. The height at this point is also the function height. So R1 is actually the function's height at whatever this point is. I'll repeat that. The distance from here to here is R1. The distance from here to here is whatever the function height is at my x-coordinate. In this case, my x-coordinate is x sub k minus 1. What that means is that my radius is actually f of x sub k minus 1. You plug in x sub k minus 1 into f, you get the height at that point. That's your radius. How about the height here, from here to here? Well, look. That's just the height of the function. That's the height of the function, whatever x-coordinate I'm plugging in. In this case, it's x sub k. So R2 is f of x sub k. Oh, now how about L? What we call L is the diagonal distance of our frustrum, how far it is from here to here. Now, fortunately for us, we've already found out how to find the length of the curve. We know that L was this. L was that, and you can get that simply by Pythagorean theorem if you really think about it. The change in height here, from here to here. Remember, if you draw a little triangle, the change in height is simply f of x sub k minus f of x sub k minus 1. So we have this, and then you square it. Pythagorean theorem, square it. Square the height, square the length. This would be delta x squared. That's the change from x sub k minus 1 to x sub k, and then take a square root of it to find the length. So Pythagorean theorem, leg squared plus leg squared is hypotenuse squared, subtract, square it, subtract, square it, and that's the L. The subtraction here is what's giving you delta x. So if we substitute all of this in, we have pi. R1 sub k is the same thing as that, and R2 sub k is the same thing as that. So we're doing our substitution. We've got R1 sub k, okay. R1 sub k plus times all of L sub k. We have pi, pi, R1, R1, R2, R2, L, L. Don't forget to square. Now this is all well and good, but we can't do anything with this unless we deal with this part, and unless we deal with this part. So we're going to look at this part right now. This is kind of a reaffirmation that we actually can find length. So basically what we realize is that this, by the by the mean value theorem, we can find a point within this. Refresh your memory with the last video. If you weren't able to find the length, if you haven't watched that yet, please watch that. How to find the length of the curve. Because what this is, by the mean value theorem, says if I manipulate this and have the slope between 2 points, I can find a certain point, xk dot, which is between x sub k and x sub k minus 1, for which the slope of the function is equal to the slope between the 2 points. In other words, the derivative at xk dot equals the slope between 2 points. So what this translates to is that thing. No, that's it. And that, you'll remember this. This is the length from last time, or from section 5 point, earlier in the section. So we'll factor out again. Notice that that's a square root of two things that are being multiplied together. We can split up those products. So we'll take the square root of this, leave it. We'll take the square root of this, that'll be delta x sub k. We're almost done. Now I'm being a little sneaky here. What I'm going to do is think about just this piece for a second. Now just this piece, I'm going to manipulate it. I'm going to multiply by 2 and by 1/2. Now when you think about that, 2 times 1/2 gives you 1. So I'm really only multiplying by 1, but I'm doing it in a very special way. Now what is this? Ignore the 2. Look at the 1/2 this. If you add two things together and divide by 2, you get the thing that's right in the middle of it. What you get is the average. So basically what we're having here is the average of the heights, the average of them. Now, what I'm going to do is let another arbitrary point, we have an xk dot already, I'm going to choose xk dot dot to be that, I know it's weird, and that other arbitrary point. So I'm going to say there's some point, I'll explain it. There is some point xk dot dot. On this interval, for which f of xk double dot equals 1/2, equals the average, basically, the average height. Here's what it says in English. It says, if x is within some interval, and k is between f of a, b, and f of a, and f is continuous, f of x has to equal k at some point x. In other words, it says intermediate value theorem. Basically says this thing, this is what I'm using in English. It says, hey, pick a point between here. Pick some point between there. Call it x. We're calling it xk dot dot. So maybe I'll put the dot. It says, if f is continuous, then there must be some point, and it must be between here, so that when I plug this into my function, it gives me exactly this height. Let me show you. It says there's going to be some point. I think I put the x dot in the wrong place. There's going to be some point, x sub dot dot, for which you can find the average. Look what we've done. We've taken the average of f of a and f of b. That's the height right in the middle of it. That's actually exactly what this is right here. That's the average height. Average height. We're saying that if this is continuous, then there is some point that you can plug in that's going to give you the average height. Let me say that again. This is the average height. Average height. There must be some point, since f is continuous, so that I plug in that point between a and b, and it gives me out the average height. It says this is going to be there. We're calling it x dot dot. Hopefully you understood that. If you didn't, I'll go back and watch it again, I hope. This is just average height. It's continuous. There's got to be a point that I can plug in that gives me average height. There's got to be a point that I can plug in that gives me average height. So that's what that says. It says that there's some point that I can plug in. It's between here, and when I plug it in, it gives me the average height because f is continuous. It has to happen. So I'm going to let this become 2 times f of xk dot dot. So let's see, we're almost done. We have now a 2, a pi, a 2, f of xk dot dot. That's all this. Times, we already had the length. times delta x. Delta x is now outside of our square root. Remember, we took the square root of the delta xk dot times delta xk squared. So pretty close to done. We'll make this a little bit prettier here. Notice that this is just the approximation for one of them, just for the kth frustrum. Now, in order to get all of them, we're going to add them together. So this was one of them. That's one individual frustrum. To find all of them added together, add them all up. Now, that's an approximation right now. To make it exact, we want to say, no. There's not just a finite number n. There's an infinite number of these frustra. That means that all of those xk minus 1 xk is going to get smashed together. Everything's going to get super close. So it's not going to make a difference that we chose arbitrary points within there. It's not. If we take a limit as n goes to infinity, right now we see an integral. We say that the surface area equals, this becomes an integral from where you start to where you stop. 2 pi constant, f of xk double dot, f of x, times square root 1 plus f prime of x squared delta x dx. This is how you find the surface area of revolution about the x-axis. Notice about the x in terms of x, just like the disc and washer, just like that, just like the length of a curve, x. Notice this is exactly what we started with, right? It's just, I mean, can you see it? Can you see what it's doing? It's saying circumference, just like we started with today. Circumference times the length. We knew this from intuitively, just from before. That's the length. If we want to do it on the y-axis, formula is going to be very similar, only it's going to be in terms of y. So let me write that up for you, then I'll be done. That's the full idea. Hopefully you got it. All right, so last time we talked about what we're going to do right now. We're going to take this curve and we're going to revolve it around an axis, but we're not going to look for the volume. We're going to look at the surface area. Again, we're not counting the ends. Those are just a basic geometry problem. We're not going to count the surface area of the circle or the circle. You can do that just with geometry. Take 2 or pi r squared. R would be your f of x at that point, at B and at A. And that's pretty much it. So we're really worried about the surface area of the revolving figure. Do you understand the idea here? Now, again, I'll mention this. The previous sections, you guys have not had that. So if you want the full explanation, rewind the video, go watch the video. That's the full explanation. What I'm giving you is a very simplified version of that. And here's how we're going to think of it. If the cross-section of this figure is a circle, and we can find the circumference of a circle, then what the surface area of a three-dimensional object is basically the circumferences of an infinite number of circles added together. Or in other words, the circumference times the length. That basically gives you surface area of like a cylinder. If you took the circumference times the length, would you not get a surface area of a cylinder without the ends? You get the surface area. Now, we don't have a cylinder, but we have kind of a changing cylinder. We have something that goes like this. So that means if we can integrate it little by little. Take the surface area here and here and here and here and add them all up. And that's basically the idea. So idea is surface area is circumference times length. So in other words, circumference of something is 2 pi times whatever the radius happens to be. So circumference, that's pretty easy. That's 2 pi r. The length, I'm going to leave that with a letter L for right now. Now, could you tell me, what's the r that we have for our figure? What's the radius there? Yeah, we've done this a couple times now. The radius is f of x. So instead of 2 pi r, if I'm dealing with my function, I'll have 2 pi times f of x. Well, for sure, because the distance from here to here, which is our radius, is also, for any value of x, the function at x. So the radius is the function at x. Now L. Notice that what we're doing is we're taking the circumference at every point, that happens to be the circumference at every point, x, times whatever the length is for the whole thing. Now the length for the whole thing means what's the length of the function for the whole thing, and that's something we just finished doing. In fact, if you looked over your first part of your homework, that's this. That's the square root, remember the square root thing? 1 plus f prime x squared dx.
Don't need an integral.
Well, we're just having an idea right now. Do you feel okay with the idea of the circumference here? That is circumference, 2 pi r, where r is f of x. And do you feel okay with times the length, where that is the length?
Why couldn't you just use the bounds to find the length? It's like, I'm not sure if I see why you need the length formula plugged in.
Because that's a great question. His question, as I understand it, is why can't you use just the difference or the distance from A to B? Why can't you just use that? Well, a straight line is the smallest distance between 2 points, correct? Is that a straight line? So this distance is not just B minus A. It's not that easy. This goes up, it goes down, it's longer than that. Does that make sense?
Yeah.
So I can't use B minus A because that would imply that I actually have a cylinder. I do not. I don't have a cylinder. Okay, what we have is a thing. It's longer than the cylinder would be. Yes?
When we're adding to the circumference, or multiplying the circumference, does that mean we're looking at the line in three-dimensional space now?
The circumference?
Yeah.
Yeah, this is definitely three-dimensional. This is a three-dimensional figure. So the circumference is taking this, taking every cross-section and finding the circumference of that.
Okay.
So we're revolving around the x-axis. So it's saying, take a cross-section, okay? Find this, the cross-section is going to be a circle. It's very similar to volume, only we're not talking about the surface area, we're talking about the surface area of the cross-section, we're talking about the circumference of the cross-section right now. So you take a cross-section, find the circumference, it's 2 pi r. Integrate that across the length, so basically multiply by length and add them all up, and what you get is circumference plus circumference plus circumference plus circumference plus circumference. Again and again, repeated addition of circumferences that are actually changing. That requires an integral and a limit. So here's circumference times length, here's circumference, here's length. In order to get the dx though reasonably, I can't just say dx. Okay, Joe was right, I need to have an integral. So surface area, when I get it all said and done, is an integral from A to B of this. Now, a question. What axis did we just go around? Notice how it's in terms of x. So Most of our formulas are like that. If you go around x, you have it in terms of x. If you go around y, you have it in terms of y. What's the only one that's not like that?
Conical.
The shells. The cylindrical shells is the only one that's not like that. So that's the one to watch out for. So if I say bicylindrical shells, if you're going around the x, it's in terms of y. If you're going around the y, it's in terms of x. Those are the different ones, okay? Everything else is basically you're going around the x, you want x's. You're going around the y, you want y's. Discs and washer works like that. Area between two curves works like that. This length of a curve, that doesn't matter, but this works like that. The surface area revolution works like that. The only one that doesn't is the cylindrical shells. That one is reversed. You're going around the y, you want in terms of x. You're going around the x, you want in terms of y. Rich, if you feel okay with that so far. All right, so this, make a note, this is around the x-axis. I can go around the y-axis, just got to switch my variables. This one would be for around the y-axis. That's basically it. That's the last formula you have to deal with in this particular class. Nice? Nice. Yay! Yay! Can you see what the parts are? Can you see that this is actually circumference of every little circle at x? No problem. That's circumference. This is the length of the entire curve, and in order to find surface area, you multiply the circumference times the length. We have to integrate because it's changing. That's what the integration does for us. It breaks it up little by little, adds every single little piece. But that's basically the idea, circumference times length. Again, if you want a more explicit definition of this, I break it down piece by piece. You can go online, watch the previous section, and then hopefully you'll be able to follow the actual calculus behind it. This was kind of a logical explanation, not a very serious explanation. Could you follow the not very serious explanation? Okay, go watch the serious one now. That'd be awesome. Now, I'm guessing that you're going to want a couple examples. Would you like some? Let's find the surface area of revolution that's my theme music. Of y equals x cubed between x equals 0 and x equals 1 when we revolve it around the x-axis. Oh, tell me something. Before we begin the problem, is my function okay if we're going around the x-axis for surface area? Is it okay? Cool. Would it be okay for discs and washers finding volume? Would it be okay for cylindrical shells? Okay, good. So you're getting the hang of it. Cylindrical shells is the one where you have to have it in terms of y. Everything else matches up with the axis. You're good to go. Now, can you set up the integral? Before you set up the integral, let's look at the formula. We're using this one because we're around the x-axis. What might you want to do first before you start just plugging random things in? The derivative is a must, so you got to be able to take that derivative. So let's go ahead and find, we know that y equals x cubed. Let's find the derivative. Y prime equals what? Yeah, don't forget about the square. I know that some of you go very fast and you forget some of these constants. Those constants are going to be huge in these problems. So basic derivatives are a must for you. There's not going to be anything ridiculous like chain rule, quotient rule, things like that within this. Otherwise, it would be pretty tasking. I mean, it would be very, very hard. But be able to take a simple derivative. Now, let's continue to set this thing up. Surface area. Start me out, folks. What am I going to have from where to where?
0.
Yeah, notice it's in terms of x, correct? And that's what we wanted for our going around the x-axis, so that's perfect for us. If this wasn't, or look at, if this was going around the y-axis, I would have to change x's into y's for this. So here I have 0 to 1, not too bad. Continue, what else am we going to have?
2 pi.
2 pi is going to be there. 2 pi comes from the fact that we're taking circumferences, that's where that's coming about. What now? Where are you getting x cubed? Yeah, that's what that says. Take your function, whatever it happens to be, in terms of x, because we're going around the x. Then what? Square root. What's inside my square root?
1 plus 3x squared.
Where's 3x squared come from? That's the derivative. We already found that's why you find it first. And then what? Oh yeah, don't forget to square it. You forget to square it, you pretty much can't do that integral in this class. So don't forget that. dx. Again, around the x. Do y'all feel okay with the setup? Yeah? Let's go piece by piece, step by step, and figure out this thing. What are you going to do first, do you think? Okay, we can pull the 2 pi out. I like that idea. Go from 0 to 1. In fact, you know what? I think the formula in some books actually gives a 2 pi in front of it, which is appropriate. That's just fine. I like to show it here because you see where the part is. But you can always pull that 2 pi out. It's a constant. It's being multiplied. No problem. What now?
I would use x to the cube, and I'd also do substitution.
Well, before we even look at that,
I'd do square your 3x squared.
what am I going to get when I square the 3x?
9x before.
Good.
And then you do your substitution.
Cool. Now we look at it as an integral because that's what it is. We say, how in the world can we do this integral? We've mastered that stuff already. What type of problem is this for you?
Substitution.
An easy one, because it's really smacking in the face, right? It's got to work out. It's something we've done in this class, or we can't do it. There's no more integration techniques for first semester calculus. You have them. So you either have to manipulate it somehow, which I've shown you a couple ways now, especially with the length of the curve. Oh my gosh, those are pretty heavy duty. Or use some sort of a substitution. Which, do you see the substitution is in fact going to work here? We have an x to the 4th and an x to the 5th. It's going to work. It's going to work just fine. So let's use our substitution. What is your u for this?
1 plus 9x to the 4th.
Yeah, you pick the whole thing inside that square root. If that's the case, du equals 36x to the 3rd dx, and we have du over 36x to the 3rd equals dx. What else might you want to do? Do you guys like changing bounds? I like changing bounds too. It makes it easier later on. So let's take our x equals 1 and our x equals 0. Let's change those bounds. If x equals 1 and u is 1 plus 9x to the 4th, how much is our u going to be?
10.
Perfect. Not too bad. If x equals 0, how much are u going to be?
1.
Not bad either. Hey, we're about ready to go on this thing. We've got our 2 pi. We're not going from 0 to 1 anymore. Those were in terms of x. Those are our bounds in terms of x. We want to change to u, so let's change our bounds as well. We're going to go not from 0 to 1, but from 1 to 10. Do I still have an x cubed? Do I still have a square root? What's inside the square root? Yes, I am. du over 36x to the 3rd. That's where we make our substitution. Dx equals du over 36x to the 3rd. Tell me some cool things that happen here, folks. What's happening? That's what we had to have happen, right? If we couldn't get rid of those x cubes, basically stuck. So done and done. What else are you going to do? Don't forget about the 36. That's important. So if we lose that, yeah, the 36, and it's going to be 136, yes, but don't forget about it. So we pull out the 136. You have a 2 over 36. What you're going to have up front is pi over 18. You okay on the pi over 18? So combining those two fractions, still an integral, 0 to 1.
I'd turn around, 1 to 10.
Oh, good catch. I was actually testing you. Good job. You'll never know. 1 to 10. What's on the inside of our integral?
1.5.
Good, okay, so we gotta make sure it fits our integration table. And we're in DU, which is great for us. So pi over 18. U to the over,
Or, yeah, or 2/3 to 3/3.
so pi over 18 times u to 3/2 over 3/2. Of course, we're gonna make that fraction look better. We're gonna make this, I'll do it in 2 steps. Pi over 18, 2u to the 3/2 over 3, just fine. We can simplify the 2 with the 18. We'll end up getting pi over 27, u to the 3/2, and we'll be going from 1 to 10 as our integral said we would. Can you please explain to me why I am not plugging this back into here before I'm evaluating? I did change bounds. If I hadn't changed bounds, that is what I would be doing right now. You got to take care of this operation somewhere. It's either before you do the integral or after, but somewhere it's going to happen. By show of hands, how many feel okay with the calculus? Basically done with the calculus. Now just evaluate. We're going to take 10 to the 3/2 minus 1 to the 3/2. Ten to the 3/2 is going to be 10 root 10. Minus 1. There's a variety of ways you can write that. You can write that 10 pi root 10 over 27 minus pi over 27. For right now, can you just verify that this is okay and leave it like that for me? Do you feel okay with leaving it like that? It's just as valid. It's as simple as we can make the radical, 10 root 10 minus 1. You can't take anything away from that. What you could do is just distribute in that pi over 27, and that's about as good as you could get. You get 10 pi root 10 minus pi all over 27. So the other way would be for some reason this looks prettier than that to me. So either way. Yes, no? Feel okay with it? Would you like to try one more? You guys alive today? Not too bad though, is it? Not too bad. Not too bad at least. The integrals have to work out, which is nice. Are there any more questions on the explanation before I erase it? Anything? All right. Okay, one more. Let's do the same thing. Find the surface area of revolution of y equals x squared between x equals 1 and x equals 2 around the y-axis. Is someone on the right-hand side, my right-hand side, tell me what's wrong. What's wrong right now? It's in terms of x. And what do we need it to be in terms of? For the surface area of revolution, that's exactly correct. So right now we have some problems up here. We have, in terms of x, we have, x and y. Those things don't match up. So you're going to have to do a little translation. Notice that area between two curves. It's whatever axis you're relating it to, that's what your variables have to be in. Same thing with disk and washer. Same thing with surface area revolution. The only one that's not like that, again, is cylindrical shell. So be careful on this. This is not set up for around the y-axis. How do we set it up for around the y-axis? Solve for x, put it in terms of y. That's the same thing, okay? So first step, you know what I'm going to do? I'm going to deal with these before I get too crazy on this stuff. How can I change x's into y's? Say what? Y square them. Okay, great. So square them because when I plug them into my function, that's what I'm going to get. Notice it says y equals x squared. It's giving you x's. Just plug them in. If x equals 1, then y equals... And if x equals 2, then y equals 4. Perfect. Now we have bounds in terms of y. Still okay? All right, let's continue. How do we get in terms of y? If we do square root, we have y equals x squared. Take a square root of both sides with a plus and minus, and you get x equals the square root of y plus and minus. Don't forget. Well, explain to me why I can forget the minus here.
That's right, for surface area, you have a negative surface area.
Not quite that.
That's where you're talking about order of functions, or the things that vary that.
Okay. Well, firstly, because firstly is this. If I'm revolving x squared, right, around the y-axis, I only need half of it. So if I'm revolving a whole, you realize that's my picture, right? I'm taking this thing and spinning it this way. Won't half of it make the same shape as the whole thing? Plus, think about my bounds, my original bounds. I'm talking between x equals 1 and 2. That doesn't have this part of it. That's just this part of it, not this over here. So it's saying, yes, this would be mathematically correct. However, it's out of the bounds of my integration. My function's not even defined right there for this integral, so I don't need this half. I don't need the negative part of that. Did you understand that logic? Okay, so we don't need that just to answer a question you might not have even had, but there it is. Are we set up? We're going around the y-axis. It's now in terms of y. That's great. We have our bounds in terms of y. We should be about ready to set up our integral. Just tell me one more thing we got to do before we get to our integral. Let's take the derivative. What is my derivative?
1/2 y to the negative 1/2.
Perfect. Yeah, exactly right. Excuse me. So, since we're looking for surface area of revolution, we know it's around the y-axis. Let's put everything in terms of y. It goes from 1 to where? Good, because we're going around the y. It has to be in terms of y. 2 pi's got to be there. What's the next thing I'm going to write instead of the 2 pi? Oh, next to the 2 pi. Say what? Square root of y, because it's in terms of. It says take the function in terms of y. Before you take the derivative, this would be like g of y. This would be like g prime of y. Function itself. Then we go ahead and we multiply by what?
Square root of 1 plus
1/2y.
1 over 2 root y.
Okay. This thing, right? Don't forget to square it. Man, I think it's nasty if you forget to square it. It's wrong and it's nasty. That's the worst kind of wrong to be. Show of hands, how many people feel alright with getting that far? Yeah. You can make something nasty and it's fine if it's right, but getting something wrong and being nasty and working on it, oh man, you don't want to do that, do you? No, you don't want to do that. At least I hope not. Well, let's work on this thing. It's going to take a lot of algebra, but not a lot of calculus, honestly. A lot of algebra. Let's pull the 2 pi out. Let's go from 1 to 4. Let's have a square root of y. Let's have the 1 plus square that thing. What do you get?
1/4 y to the -1 plus 5.
1/4 y to the -1.
Be very careful. Be very careful. The 1/4, very good. The y, -1/2 times 2, not adding, times. -1/2 times 2 is -1. So you're not going to get 1/4 y. You're going to get 1 over 4y. Do you see it? Or you can do y to the -1 over 4, but you're going to change that. So 1/4, I'll say y to the -1, just to follow the steps down. What that becomes is 2 pi, 1 to 4, square root of y, square root of 1 plus 1 over 4y dy. Take a look at it, see if you can follow it down. It's a lot of algebra with those negative exponents. I know they can catch you sometimes.
Why do you need to lower it down?
You'll see. You'll see. Just a second. You okay with it so far? So this, square it, 1/4, square it, -1, y to the -1, denominator. You okay with all of it? Okay, now, I'm about to do some fancy math. Fancy pants math. There's a few ways to do this. I will be showing you one way. Maybe I'll show you both ways. We got some time. Maybe I'll show you both ways. Here's fancy math way, and then I'll show you non-fancy math way. Either way works just fine, okay? So 2 options. Fancy math. You ready to see fancy math? Here's fancy math. Fancy math way says, take the 2 back in there, but call it the square root of 4.
1 to 4.
Oh shoot, I'm on the last row still. Good catch. Here's fancy math. Take the 2 back inside, but call it the square root of 4. You okay with that so far? Is it still 2? Why am I doing that? I'm doing that because I know that the square root of 4 and the square root of y can be multiplied together to give me a square root of 4y. Why did I pick 4? Why? Well, look at that. I have a square root times a square root, and what I know about that is that I can multiply square roots times square roots, and the radicands that's inside the square roots can multiply together. So if I do this, hopefully you can see this. 1 to 4, big square root, look at 4y, and what's going to happen here? 4y times 1 gives you 4y. 4y times 1 over 4y gives you... Done. Practically. Anyway. Practically done. That's a fancy way to do it. Take the number inside of there, call it, make it up, make it a, instead of 2, square root of 4. See if it simplifies something. In this case, it did. That was kind of a nice, easy way to do it. Were you able to follow it? Let's say you didn't see it, because chances are you're probably like, oh my gosh, I wouldn't be able to see that on my own. Can you do it differently? Yeah, I believe so. We're distributing right here. 4y times 1 plus 4y times 1 over 4y. The 4y's are going to simplify out. Okay, so this was like, I'll call this here's star 2. So from this point, if you don't do what I just did, what you end up with is square root of y, 1 plus 4y, I'll rewrite it, 1 plus 1 over 4y dy. What you have to do is what we've done similarly. I just showed you a nice step that didn't require you to do this, but you can do it in a way that I think hopefully should be familiar to you. Find the common denominator here, over here, 4y over 4y plus 1 over 4y. Like that. Find that common denominator. You got me still? Put the fractions together. You remember doing this? It's very similar to something we've done before, where we had to break up that square root by a quotient. Can we do that now? Have I lost you? Are you with it? Do you see what we've done so far? Found a common denominator, put the fractions together. That way we can separate them. So 2 pi still. Square root of y times square root of 4y plus 1. There's nothing you can do with the square root of 4y plus 1 right now. Nothing. You can't split that up. However, this is the square root of 4y on the denominator as well. Now, when you think about the square root of 4y, what that is is 2 square root y. See how to get the 2 square root y? Yeah, you see we're going to get the same thing. It's kind of cool. Either way you do it. This has a few more steps. I mean, really, it's just like 3 steps, 5 steps. But you're going to get the same thing. Whatever way seems easier, I don't care. But I just gave you another option over here. This is kind of the fancy pants type of math. Ooh, I want to be fancy. Do the fancy. If you don't want to be fancy and you get this, do this. I really don't care as long as you get the right answer. Tell me what happens here, please. 2's are gone. Yeah. Constant, constant. Very good. What else?
Square root of y.
That helps you a lot, doesn't it? Because if you don't get rid of that square root of y somehow, you're smoked. Otherwise, you'd have to look for some substitution, and that's just not going to happen with this example. So now we're left with pi 1 to 4 square root of 4y plus 1 dy. Now, will a substitution even work? What's the derivative of 4y plus 1? 4. Does it have a y in it? Then of course it'll work. You always neglect constants with your substitutions. Constants don't matter because you're just going to pull them out front anyway, right? So will a substitution work here?
Yes.
Absolutely. What's the derivative of 4y plus 1? It's 4. There's nothing that you need to simplify out. You're going to pull the 1/4 out of your integral anyway. So let's do that here. U equals 4y plus 1. You generally pick the thing that's inside your problem. And right now our problem is a square root. Don't forget that you do need a substitution though. You absolutely must. Du equals 4 dy. Du over 4 equals dy. What else do you want to do right now? Let's do that. I'm sorry, when u is 4, you get how much?
17.
And u is 1, sure, 5. So those right there, those are our new bounds of integration. We're not going to have to substitute back in for x's later. We have these in terms of u. We're good to go. So let's rewrite our integral real quick before we do it. We'll have a pi. We'll have this integral from 5 to 17. Because we just changed bounds. Square root of u du over 4. Don't forget that the dy becomes a du over 4. So 4y plus 1, u. 17 from the 4 when we plugged it in. 5 from the 1 after we plugged it in. Du over 4, that's equivalent to dy. So we have the appropriate integral right now. Quick head nod if you're okay getting that far with the calculus. Yes, yes, yes. Okay, cool. Are you ready to do the integral? Yeah, it basically fits our integration table. Maybe I'll write it one little different way here. Pull that 4 out in front. We have pi over 4, so pi over 4, u to the 1/2, going from 5 to 17. Basic integral. Now we all know the integral of u to the 1/2 is u to the 3/2 over 3/2. That is pi over 4 times 2 u to 3/2 over 3. Hey, we got to simplify that, plug in some numbers, we'll be good to go. So 2 with the 4, we're going to get pi over 6 u to the 3/2. Oh, what am I going from 5 to 17? Now we're going to plug in 17 to the 3/2 power. 17 to the 3/2 power. That's right. In fact, some books leave it just like that because they're like, seriously, you're going to go any further than that? You know, what are you going to do? Well, it doesn't really matter. If you can make it down that far, I know you know what you're doing, okay? These numbers generally are not very nice. You're dealing with a length, right? Which is why you get the weird 17 root 17 thing and the 5. Remember those from the length of the curve? We get a lot of those. You get those a lot with that. So with this, you're going to get those a lot as well. You're just multiplying by circumference right now, length times circumference, basically. So you get a lot of this. So leave it like that, or go one step further.
Can we leave our link problems in the same format with exponents instead of breaking it down further?
By the way, do you know why 17 to the 3/2 power gives you 17 root 17?
It's a square root.
Okay, it's because you have 17 squared times 17, square root of 17 squared is 17, but you can't take it the next one, so you have 17 root 17. That's the answer. Would you raise your hand if you feel okay with what we talked about so far today? All right. Well, are there any questions?
The last
I
time-
hope you enjoyed calculus.